A very warm wishes to everyone. So I will be presenting on the X-rays, its diffraction, how it is produced, the use of diffraction techniques in finding those crystals, those applications because of which we have those X-rays. We are kind of interested in knowing how it is produced and how it works. So in the corner you can see we have a picture over there which you may be familiar with most of all, that this is a Bragg's law, which is going to signify using this that interplanar spacing between those distance, which is d, the upcoming wavelength which is hit on the plane of the crystal forming an angle theta is of lambda. So this all satisfies a condition which is known as, for you all, 2d sine theta equals to n lambda, and this condition is what we call as Bragg's law. Whenever this condition is satisfied, the diffraction takes place, which is the necessary condition we will be using in the future slides. So this is the requirement for the diffraction to happen. So let's move a bit. Now if you can see, we have how the production of X-rays takes place. In this setup you can see we have a focusing cup. This yellow part, which is used named as number 1, is a focusing cup. What it is used for? It is used for making this electron beam at a focus at this point of a target which is number 5th is used, this focusing cup. So this filament of a green part you are seeing, this one naming number 2, is a filament made of tungsten. This tungsten will be heated by the current and will help in producing the electron, which is in turn used for electron beam, which is marked as a number 3. The all over empty spaces we have is of 4, which is a vacuum. As I mentioned you, this is target. The target is also made of tungsten. The 6th part is of orange color, is used for made of copper stem, used for passing out the heat. And the X-rays liberated, I marked at 8, the zone white part is passed through the beryllium window, which does not interfere much for the passing of X-rays. So let's see how it works. One more thing I would like to mention to you all is uh, this setup is connected using a battery of a high potential. Why we use this high potential, we will see now. This current is passed through a tungsten filament which heats it up. So for heating the tungsten part we used current, and this current will be produced to this battery only, which has to be part of the cathode and anode. The increased energy in heated filament enables electron to release through thermionic emission. Those releasing of electron through the tungsten is named as thermionic emission. The released electrons are attracted towards the anode which has a positive charge will definitely attract the negative electrons and hit the tungsten target, which is a focal part. You may be worrying about why this tungsten part is slightly bended in nature. Why can't we keep it in this way so that electron beam hits like this? So the answer for that is we have to keep it in a little bent way. As you can know, the focal part should be of very small size, but if it is too small it will maybe heated out or burned out. But to be at a safer side we have to get it this length, and if we bend it a little bit we have a reduced aperture which will help us in creating a better beam and a thin beam. As in a daily life example you can find it out when you people take selfies. By taking the camera in front of you, you may be appearing a little bit thicker, but if you put your camera in a little upward direction in a bent way you may appear a little thin. So this is the reason, so that is why why we are using that focal part in slightly bent way rather than making it absolutely straight. As the electron bombards the target, they interact via Bohm-Armstrong and characteristic interaction, which results in the conversion of energy into heat and X-ray photons. What happens is we have those electrons in that atom of a tungsten. Whenever an electron beam comes out, it interacts with the surrounding of the atoms. It leaves the atom and maybe getting into the other atoms and all. They will produce out the source for some sources of energy which will be coming out through in the form of photons, and these photons are responsible for and helping for us to for producing X-rays. This is what the Bohm-Armstrong interaction is. So what we are now in condition like this copper anode, this is used for liberating out the heat outside because of tungsten being very highly heated because of electron being hitting on them. And why we use this tungsten is one of the question maybe with you. The reason we are using this tungsten is it has a very good melting point. It has a good out of thermal conductivity which does not and it has a good vapor pressure also. It has a good vapor pressure. What is the need of vapor pressure here? Its vapor pressure will not uh, put this vacuum around you in something like, it will not disturb the vacuum, it will just resist the change for the vacuum, so it helps in maintaining those vacuum part. Now whenever this electrons hits, the photons are coming out and these are result in those X-rays. The X-ray photons are released in the beam with the range of energies X-ray spectrum out of the window of the tube and from the basis for the X-rays image formation. This is the thing you can see now. The cathode is releasing out this electron in a focus by the focal plane, hitting on a tungsten part which is slightly tilted, releasing out the electrons, and this tungsten part, the tilted part is now giving out the X-ray spectrum. This setup is connected. This setup is connected to high potential. Now moving on, X-ray diffraction. In 1912, von Loewe suggested that X-ray can be diffracted using crystal. So what was the need of that? To study the crystal structures and all, we can use this diffraction technique. So how did we get that we can use that? That was because it was possible because of the fact that order of interplanar spacing of a crystal and X-ray wavelength order are both of 1 angstrom. So this is the basic condition we use in diffraction, that the falling wavelength and the radius of the on which it is falling should be of diameter on which it's falling is of approximate wavelengths. When this is the basic condition for the diffraction. So as we found that this condition is matching, so we look forward for the diffraction techniques. So we have the few diffraction techniques which are Loewe's X-ray diffraction method, rotating crystal method, powder X-ray diffraction method. These all the diffraction methods are used for determining us these crystal structure, crystal lattice, unit cells and all. So we will find how it helps and how it may be useful for us to produce out this result. So first of all what we have is Loewe's method of diffraction. You can see, I will first of all explain you a little bit setup. In this setup, white X-ray beam through that only tube is passed. This passes through the colorimeter, producing a thin beam of X-rays falling on a single. So This beam, when passes through that single crystal which is kept, either it will deviate from the crystal due to the interplanes, or it may get reflected back, or it may pass undeviated. So for undeviated part, we have a hole over there which releases those undeviated electron beams, X-ray beams out, and those diffracted part falls on the placeholder which is capped, which is a photographic film sort of, which creates a pattern, and those reflected back beams are also creating a pattern on this reflection pattern. And this all is placed upon this basis, having a goniometer placed here. This goniometer is used for measuring those angles. This gonio itself means the angle, so its goniometer is used for measuring angle. So this crystal, you can see this one is used for transmission, the X-ray beams after transmission on making up some pattern, and this and the reflection back, we're creating some sort of patterns. Moving on, we have this Lois method. This method is mainly used to determine the orientation of large single crystal. So we have a limitation over here that we can use a single crystal only. While the radiation is reflected from or transmitted, as I told you, some radiations get reflected and some get transmitted through a fixed crystal. The diffracted beam forms arrays of spots. So these spots, as you can see, being created, these spots are the reason why we can help to find out about the crystals that lies on the curve of the film. The Bragg angle is fixed for every set of planes in the crystal. Each set of plane picks out the diffracted and particular wavelength from the white radiation that satisfy the Bragg's law for the value of d and theta involved. So the word we have used is white radiations. This is because we are not putting a single monochromatic wavelength of X-rays. We are putting some various wavelength of X-rays on that single crystal. On the single crystal which has a fixed angle, so theta is fixed, but lambda is varying. But since the distance d is also fixed, we have in the 2d sine theta equals to n lambda 2d sine theta, all are fixed, but lambda is a variable over here. So due to this variable lambda, we can have a different conditions and different spots at a different wavelength, which will help us to find out patterns or the array of spots on the film. Lois method. In this method of a diffraction, continuous X-ray of some range falls through the pinhole arrangement on the specimen of 1 mm cross 1 mm cross 1 mm dimension. Then reflection plane chooses a particular wavelength for which Bragg's equation is satisfied. So I will tell you this in further. Now the diffracted rays falls on the two near photographic plates, which is like I told you, the slip of one is a reflection and one is of transmission. So the rays on this and this create some of the patterns, which is reflection pattern that's obtained on the two film consists of series of spots. So as you can see here, this one, this has a series of spots line. These spots will help us to create find out the symmetries and find out the about the crystal, like, let me erase. So if I have, suppose, this folds, so these lines are signifying those folds. This, if we have 1 2 3 4 4 fold symmetry, so we can express our conditions and our results in the four-fold symmetry, which will help us to know about the crystal and its unit cell. So advantage is of uses used for rapid determination of crystal symmetry and orientation. It can be used to establish the shape of unit cell. Now we have another diffraction technique, which is the rotating X-ray technique of method. In this method, single crystal specimen is rotated about a fixed axis with the help of electric motor. As you can see, this is the shaft which is rotating out, and this is the specimen kept here. This is also a single crystal this time, and a pinhole is used to pass the X-ray which has to enter in it. But this time we are passing it through a filter. What this filter will do is this filter will be producing a monochromatic wavelength of X-rays. So we have the fixed wavelength here, so we have a fixed D. What will be changing will be the D due to this changing of rotating of motor. So we have 2d sin theta equal to lambda. Bragg's law will satisfy for particular wavelength or particular theta here. So these rays will produce out some of the patterns in the upper or the lower region, and which will not be producing leaving straight, will give out from here. As the crystal rotates, different sets of parallel planes get positioned so that Bragg's law equation is satisfied. As I told you, a monochromatic beam made using the filter of X-ray is allowed to fall on the single crystal specimen. In this method, a single crystal is mounted with an axis normal to the monochromatic X-ray beam. As you can see, this X-ray is this one. You can see this is the plane of filter which is perpendicular to the X-rays. So that is what it was saying. A cylindrical film is placed around it and the resistor is rotated about the chosen axis. So this is the cylindrical film outside. This is the cylindrical film outside, you can see, and it is mounted outside this cylinder, and the rotates about this axis. What we are seeing is this axis, rotation of axis, and the axis of cylinder both coincides. As the crystal rotates, sets of lattice planes will at some point make the correct Bragg angle for the monochromatic incident beam, and at that point a diffracted beam will be formed, either upside, as you can see, diffracted beam going up, or it may be going down. Diffraction pattern is obtained on the cylindrical photographic film whose axis coincide with the axis of rotation. So you can see this is what it looks like. The pattern h equals to 0 is signifying those undeviated part plane, and h equals to 1 2 has some changed HKL value h. So we can have in between these spaces, we can use these spaces the difference of h for to determine the lattice parameters. So by recording the diffraction pattern, both angles and intensity, it helps in the determination of crystal structure. It helps to determine the size of the unit cell of the crystal also. So now what we have is X-ray powder crystal method. In this powder form of crystal is used. The crystal structure crystals which we are having is crushed and made in a powdered form and kept in the capillary tube at this point P, which we are seeing here, is in where this all powdered form crystal capillary tube is placed, which on X-ray beams passing through the filter creating a monochromatic light falls on it and leaves this as either diffracted or undeviated, which undeviated part will pass through this hole and the rest of the part will create some of the diffraction pattern. So what we are changing here, as we have earlier we were saying that lambdas were changing because of which Bragg's conditions were satisfied, then the theta was changing because of rotation, but now what here we are using is the crushed form, which will help in promoting different angles at which the Bragg's condition has to be satisfied. So this is the condition here. So after this passing of X-ray beams, this X-ray beams here creates this pattern in slightly forms the patterns of cones, which cones may be of a shorter or this cones may be a bit longer in part. So this bigger and smaller cones creates a pattern. It's this on this camera sheet, thin sheet, which is placed here. So these arcs will be left over on this part. So this arcs will with this film, when straightened out, is produced in this manner. On the this black spot is where the ray was getting passed through. So distance between these two can be termed as L. So we will see what is this. X-ray powder diffraction is a rapid analytical technique primarily used for phase identification of crystalline material. Can provide information on unit cell dimension. The analyzed material is finely grounded and homogenized, and average bulk composition is determined. This method was discovered by Debye and Squire, that is why it is also called Debye-Squire camera, in 1916 to determine the structure of finely powdered crystalline material. Now this material is kept inside a capillary tube, then a narrow monochromatic beam, monochromatic is made using filters of X-rays, is allowed to fall on the specimen. This material contains variety of crystals for which we have different value of theta. Beam ID made monochromatic using a filter. Photographic sheet is used to receive diffracted X-ray. Fine powder is struck on here with a gum. It is suspended vertically in the axis of a cylindrical camera. The cylindrical camera, as I told you, that the thin sheet which we are setting up, that is the thin camera, cylindrical camera we are talking about. When monochromatic beam is allowed to pass, different possibilities may happen. There will be some particles out of random orientation of small crystal in the fine powder. Another fraction of grains will have another set of planes in the correct position for the reflection to occur. Reflections are possible if in different order for each cell. So in this also we can this cone which is making those patterns, this that cone will be that cone, let me draw it. Now this as you know, this cone which is formed will have some angle theta, but this is also theta, so it creates a 2 theta angle, and this 2 theta angle will help us in determining the relation which we are gonna use. That I told you, to between this arc the length was L, so that L, that arc which we are using, so this 2 pi r is the circumference and r is the radius of that film, cylindrical film that we have used. So this gives the relation and for the theta. Now this relation, with joining it with the Bragg's equation, that is 2 sine theta is equals to 2d sine theta equals to n lambda, and using that d which is for a cubic cell as a upon root h square plus k square plus l square, and using these both conditions, we can find that the rest of the eliminating those rest of the constant which is n lambda 4a etc., we will find the relation like sine square theta is directly proportional to h square plus k square plus l square. So this relation will give us the family of planes that we are using in that cylinder. We are getting those family of planes for which if s square k square l square has the value of 1, it can be 0 0 1, it can be 1 0 0 it, so that's why I've used this curly bracket which represents the family of plane. So this helps us in determining those crystal structure. So this had following advantages: if a powder specimen is used instead of a single crystal, then there is no need to rotate the specimen because there will always be some crystal at an orientation for which diffraction is permitted. Here, a monochromatic X-ray beam is incident on a powdered or polycrystalline sample also can be used here. This method is useful for samples that are difficult to obtain in single crystal form. So what is the application it has? It has identification of unknown crystalline materials. If we are known about the symmetries, then we could have earlier also be known. But here, determine it makes it easier as we can find the crystal structure here easily. Determination of unit cell, measurement of a sample purity helps to determine the lattice parameter ABC due to the help of distinguishing between the H and K and L, the spacing or the between them. So thank you. I would like to say then. Any questions or can be asked in the comment section.